Hi everyone, welcome to Reverse Engineering 101. I'm Samin for those of you who are joining for the first time, and I'm going to be talking about reverse engineering in today's workshop. So let's get started. So today what we're going to be looking at is what is reverse engineering, how reverse engineering is used in capture the flag events. We're going to be taking a look at Java assembly language, what registers are, how they work, and assembly instructions, and Android reverse engineering. Yeah, that's what we're going to be taking a look at today. So let's talk about what exactly reverse engineering is. Reverse engineering is taking something apart and putting it back together again to understand how it works. And the best analogy I can give that I've seen being used multiple times for reverse engineering is the analogy of taking an already built bicycle and taking it apart. Now, what purpose would that serve? Well, when you take apart a bicycle that's already built, by taking it apart one part at a time, you can understand how each of the parts works and how they contribute to the overall bicycle. For example, you could take apart the brake. When you take the brake apart, you would determine if all the other parts are there that, taking the brake apart doesn't allow you to stop the bicycle. And that would help you understand what role the brake plays in the overall bike. Which is very different from, just being given a bicycle from scratch and being asked to build it. So just like that, some useful applications of reverse engineering in cybersecurity are analyzing malware and malicious programs to understand how they work to prevent against them, breaking down code to better understand the potential vulnerabilities of a software because just like the bicycle example, this reverse engineering allows you to take apart each part of a program to see exactly what that part or component of the program does to better understand what the entire program does and how it contributes to the entire program. To understand and also, to understand how certain parts of the program work. So that is the useful applications of reverse engineering in cybersecurity. So what exactly needs to be reverse engineered in capture the flag challenges and then in general? So, usually there's some sort of code or program that's written in Java, Python, or C, or any other language that needs to be analyzed and reverse engineered. You might have binary files, assembly instructions, malware, or applications that, you need to analyze the source code for. So that's generally what needs to be reverse engineered. Skills and tools that are useful for reverse engineering, it's important to have a basic programming knowledge and understand programs and, to understand how to read them. And for that, you're going to need to know a little bit about Java, Python, C. Most of the programs are pretty self-explanatory and not too hard to understand what's going on, but it's really good to have some programming knowledge and skills. You need to understand how assembly instructions and registers work, which we will be covering in today's workshop. You need to understand memory allocation and how exactly, memory is allocated. And tools that are really helpful include debuggers, disassemblers, and decompilers. Debuggers allow you to step through program one line at a time to really understand how each line is contributing to the overall code. Disassemblers break down a compiled program into machine code, and decompilers are tools that are used to convert an executable program or a low-level machine language into a more human-readable format. So let's take a look at Java. Java is a programming language and it's used to build applications, desktop, mobile web games, and so much more. It's a very useful programming language. And let's take a look at some of the variables that are included in Java, but these variables are the same across most programming languages. So we have strings, and strings store text such as hello, and strings are always surrounded by double quotes. So if you see something surrounded by double quotes, you know that it's a string. Integers are whole numbers and decimal values are not accepted. So an example would be 100 or negative 100. Float is a floating point number which includes decimals. So an example of a float number would be negative 100.25 or 100.25. Characters are characters are just single characters, and they are represented by single quotes around them. So you have like A, or you would have like be as a single or as a character value. And Boolean is either true or false, and that can either store two states, true or false. So let's take a look at a simple PicoCTF challenge. This challenge is called Vault Door Training. It is a Java file. And when you take a look at it from the beginning, right away, if you just take a look at the entire program, you're going to see right here a password that is given to you. So you right here, and as we know, you could put that into the program, into the backend with the PicoCTF, and that is your flag. So this program is really self-explanatory, but let's see exactly how we can break it down. So these two lines are pretty standard. So every line of code that runs in Java must be inside a class. So this is a class right here, and all programs will start this way. You will see a class, and then you're going to see the name of the Java file. The name of the Java file must match the class name, and this file is called Vault Door Training, exactly like that, .java. So this, again, this is the main method, and it's required again, and you will see it in every Java program. So this is very basic code that you will see, and it's not too important to what our program exactly does. So now let's take a look right over here, what is going on. So the scanner class is used to get user input, and it is found in the Java util package, which is being imported so that we can use it. The system in tells Java compiler that system input will be provided through the console, which is also known as the keyboard. So it tells us that users will be typing in some sort of input, and the system is going to print out enter vault's password. It's asking us to give it some sort of input, and then it's going to get that user input from us. Next, right over here, these double slashes are comments. So it's just giving us some hints right over here. It's saying that the password is below. Is it safe to put password in the source code? It's not. What if somebody stole our source code? Then they would know what our password is. So it's not safe to use, to have the password stored in the source code. If you ever see a program like this, that's not a very secure program. So that's the comment, and the comments can be indicated by double slashes or slash and an asterisk, double star and asterisk for longer comments. So basically, after the comments right over here, it's checking the user input, but basically what it's saying is that right over here, it's checking for user input, and what it's saying is that the length -1, which the PicoCTF, this part right over here, and the length -1, and if you look at the overall input, it would be the last character, the opposite of this. That's not going to be checked. It will be there, but that part will not be checked. What is checked is the user input, which is the string provided right here, and if it matches with what is expected with this, then it will print out access granted, and if it does not match, then it is going to print out access denied. So let's take a look at exactly how this would work. Let's see how this program would work. Okay, so let's paste all of this program into a online Java code compiler. Okay, and I think I need to add public class right here for it to work. And then let's execute the program. It might take a little bit of some time because it's just compiling. Okay, perfect. So it's executed. So over here, we can put our input, and it says enter vault password. So now let's say we just put this value like that. Oops, I didn't mean to do that. Let's say we put this value here just like that into right over here. We're probably going to get an error because access denied, because we didn't put the PicoCTF that it expects. It expects it to be like this, PicoCTF, with the string right here. and now it says access granted. So that's how this program would work. Let's just exit this program. So that's just a little demo of how this program would actually look like. Okay, so that was this program. Now let's take a look at some additional Java programs. So I'm going to go into Pico CTF platform, and I'm going to go into reverse engineering, and I'm going to take a look at Vault Door 3. Let's open this program up, and let's full screen it and zoom into it and see what is happening. So right here is our main, just our main arguments that we expected. It's doing the same thing as the last program. It's going to check the input, but this time the input that it's checking, it's going through some sort of a, it's going to do some sort of thing to make the password stronger. So what the hint says is they've noticed some intrusions on some of the less secure doors. So they've asked, the Dr. Evil has asked me specifically to build a stronger vault door to protect his doomsday plan. I just know this door will keep all those nosy agents out of our business. So it's going to check the password, but before it checks the password, which is right here, it's going to do some sort of shifting or whatever on this password before to get it. So that exact algorithm that it's doing to the password is right over here. So let's take a look at it. So we know that our password length is 32. So 0 to 31, which is 32 characters. And so our character buffer is 32. Now our integers are the positions. So from so basically what this is saying is from integer 0 to 8 to less than 8, the buffer at that value, or at that value, it is going to be the character at that value. So from positions 0 to 8, let's type that out right here. So this is 0, this is 1, 2, 3, 4, 5, 6, 7, 8. So right over here, actually, let me see if that 0, 1, 2, 3, 4, 5, 6, 7. This will not be included because it says 0. It starts at 0, but less than 8. For every position from 0 less than 8, the password at that point is going to be equal to whatever is already in that position. So we have the first part of our password. Now, this is where it gets tricky a little bit. What it's saying is that for I is less than 16, so any position less than 16, and I plus plus, I forgot to mention, means that I plus 1, I plus 1, so it's going to be, it's going to be for, let's say for starting at 8, it's going to be 8, then the iterations are going to be plus 1, so it's going to be 8, 9, 10, 11, 12, whatever I is plus 1. So then from 8 to less than 16, which means from positions 8 to 15, those positions, what you're going to do is take 23 and subtract it by I. So right over here, we have position 8. So to figure out where position 8 exactly will go, let's calculate it. Position 8 will now be at position 15. So let's just put position 8 right over here. And position 9 will now be at, I think position 9 will now be at 14. Yep, so basically what's happening is that it's going backwards from those characters. So it's going NA underscore from the positions 8 to 15. So this is 8, 9, 10, 11, 12, 13, 14, 15. So we're just going to have it going backwards. So it's going to be NA underscore 3 L P M 1, 8, 9, 10, 11, 12, 13, 14, 15. and we just need 1 right here. So now we see what it says. It says just a simple, and now we have to figure out what the rest of it says. So let's mark the place where we stopped. We stopped right after this one, so I'm just going to put a space there. So we know that right over here is the 15th position, and this must be the 16th position. So then the next part, it's saying for any position less than 32, the value at that position is going to be 46 minus I, but over here we're not iterating that to all of them, we're doing that plus 2. So we're going to start at 16, but then the next one is going to be 18, and the one after that is going to be 20, and then the one after that is going to be 22, so on and so forth. So let's start off with 16. We know this one right here is 16. So it's saying the position of that, now whatever is here at 16, is going to be at the, let's calculate that, at the 30th position. So it's going to be all the way over here somewhere. So to make everyone's life easier, I thought that I've already solved this. So I'm just going to leave that part blank, and I'm going to tell you guys what that is. But basically, it's mapping it out. So 16 and 30 are going to go to each other. So 30 minus 16. So 30, whatever is at position 30 is going to come at position it should be 16, right? Whatever is, sorry, at position 32 is gonna come, so this is less than 32 actually, so we can't do position 32. And since when we get to 30, it stops because it's less than 32, and 30 plus 2 is 32, so we can't do that. So it's gonna have to stop at that point. So as we were looking at this, so for this one, it's again mapping them out. So 16 is going to go with 30th, whatever is in the 30th position is going to come into the 16th position. Whatever's in the 18th position is going to go into the 28th, and the 28th to the 18th. So when you map that all out, what you get is, get a 4, you skipped, and then you have R, skip, M, skip, 4, skip, U, skip, oops, 4, U, skip 7, and 9. So this is our 30th position right here, and we need 2 more over here. Sorry, 1 more over here, and then we're missing the odd numbers because we were adding each of these by 2, we didn't get to cover what's happening at the 17th position, what's happening at the 19th position, what's happening at position 21. So this one just added 2, so this one only mapped out the characters from 16 to 30, 16, 18, 20, 22, 24, 26, 28, and 30. So we're missing everything in between. So now when we get to the next part, we have right over here, from I is less than 32 and so everything that is, sorry, we already did this one. So when we get to this part right over here, what we're looking at, I is equal to 31, or I is greater than 17, greater than or equal to 17. And for this one, we're subtracting it. So we're starting at the 31st position. And it's saying that whatever the character is at that position is what we're going to put in that place, in place of that position. So we already know at the 31st position we had this F. So F is going to just go right over here. Next, we subtract 2. So 31 minus 2 is 29, which will be right over here. And at the 29th position, we have 31, 30, 29. We have a 5, so 5 will go here, and you're going to do that all the way down to the 17th position. And when you do that, you're going to get this value right here. I've already done that before, so I'm just copying it to save some time for, then after, and it's another underscore. And then right here, it is a 4. And right over here, it is a G. So basically what this is reading, it's reading just a simple anagram for you. So this is the, it's going to do that, but this is the password. So when you put the password, it expects it in this type of format. It would switch it around to protect the safety of the password, basically. So that is what the CTF will be. Of course, you have to put Pico CTF and then the 2 curly brackets, and that's how you get there. So now let's take a look at, that was vault door 3. Let's take a look at vault door 5. It's a little bit more challenging and a little bit more different. So let's take a look at this one. So again, it's very similar to the same other 2 programs. There's a Boolean, which is printing out either access granted or denied, depending on the input that it receives. Right here in the comments, we're getting a hint that there is some base 64. Base 64 is an encoding algorithm, and if you remember from the forensics, from the cryptography workshop, and we talked about it in forensics as well, encoding and encryption are not the same thing. There's no key being used. If you know what encoding algorithm is being used, it's just to preserve data or represent it in another format. It just switches the data to a different format. It's not supposed to be a secret. That's all encoding is. And base 64 is type of an encoding scheme that is used to encode data. So it says right here, base 64 encode and return base 64 get encoder. Now, I just want to point out that all of these programs, you could just run them and you would get the flag. But because we're reverse engineering, we're trying to see what each line of the program is doing, which is why we're doing it in a little bit more tedious sort of way. So let's take a look. So we know that the message is going to get encoded base 64. And this is the base 64 encoded message right over here. So let's take that and let's go into here and let's look up CyberChef, because that is a great, it has base 64 on it. And I think I shared this platform in the forensics and cryptography workshop. So we're going to do from base 64. Let's input that. And this is what we get right over here. And just by looking at this, it might be obvious to some of you, but it might not be obvious to everyone that this looks like it is hexadecimal value because of the 6E, the Fs, that looks like a hexadecimal value. So let's take hex and let's convert it into, this is not the right calculator, let's do hex to ASCII converter so we can actually get the text that we're using. We're going to get rid of all of these percentages. So it says that's the first part of our flag. So let's just put that right over here. Converting, let's make this big screen. We can see big, and that's what we get. We go back and just do the same thing with this. And it's pretty self-explanatory. This is also in hex. We can tell by the 5F, the 6D. If we didn't have that clue, we might have, I don't know, assume that maybe it's decimal, but that gives it away that this is a hex value and we get from base. And so we're not going to finish the rest of the problem. Basically, you take the last string and you also decode it from base 64, and then you convert the hex to ASCII and you would have your flag. So that's not too bad, right? That's pretty simple. So now, now that we've taken a look at some additional Java programs, let's talk about assembly language and what exactly assembly language is. Assembly language is a low-level programming language designed for specific types of processors. and it's also known as ASM. And so if you see an ASM file, then you can assume that it is going to be some assembly language in there. So let's take a look at this. This is binary. We can tell from the ones and the zeros. This binary instruction is telling an x86 processor to move an immediate 8-bit value into a register. So obviously, when we look at this, we are not computers, so it's not easy for us to understand what it's saying. But if the computer had this, it would understand exactly what to do with it, and it would execute it. Now, it can be made more human readable if we take this and convert it into, if we convert it into hex, then it can be made more understandable. So when we convert it to hex, basically what happens, we get B061. What it's saying, what now it means is B0 is saying move a copy of the following value into AL, and 61 is a hexadecimal representation of the value right over here, which is 97 decimal. So it's saying take 97 and store it into this register. Now, assembly language would be much easier to understand. It's very much more human readable. And it is what it does, it provides mnemonics, which are abbreviations for different commands. So for example, move is an abbreviation of move, MOV is an abbreviation of move for instructions, so that the machine code can be written as follows. Sorry, my mouse is sensitive. So the assembly language can be written like this. So instead of, we go from this complicated binary instruction to this, which is a little bit more, a bit better, but then we still don't know what 2 hexadecimal values really mean to a processor. But then when we get to right here, we can understand that this is saying move 61 hex into the AL portion of the register. So now, as we're going to take a look a bit more into assembly language, but we're going to be taking a look at it in this format. And this format will allow us to understand what the processor is doing and what's really happening in the backend. So it's really helpful. But before we take a look at that, we need to understand a little bit of how processors and how registers and memory really works. So let's talk about the central processing unit. We all know the role that a CPU plays in our computer. Without the CPU, our computer would just have no functionality, because CPU executes all of the instructions and everything and makes it possible for us to interact with our computer and for it to do anything. So let's take a look at the three components of a CPU. The arithmetic logic unit, which comprises of 2 separate units within itself. It consists of the arithmetic unit, which is responsible for mathematical functions such as addition, subtraction, division, multiplication, and logic unit, which is responsible for logical operations such as OR, exclusive OR, and NAND, and so on and so forth. The control unit, it directs the main memory, the ALU. It also is responsible for instructions that are sent to CPU. But what we're really concerned with in reverse engineering is registers. So registers are small, extremely high-speed CPU storage locations where data can be efficiently read or manipulated, and you can hold data temporarily in the registers. So when we do our binary exploitation workshop, you're going to see the importance that registers really play in protecting and preserving registers. It's really important to protect that space so that a hacker doesn't have access to it and cannot write their malicious code, because then the CPU gets their data from the registers and it would just execute it. So it's really important to understand how important and key registers are in reverse engineering and binary exploitation. So that is a little bit about CPU. Let's take a look at registers and what registers do. So registers hold temporary data that is needed by the CPU to execute instructions. Registers perform operations, they store resulting data. So they can only hold a small amount of data. So we have a 64-bit architecture of CPU would hold 64 bits of data, and a 32-bit architecture would hold 32 bits of data. The CPU architecture determines the design of the processor, instructions that are supported, the size of registers, and other factors. So it's really important to know what sort of architecture you're working with. And the most common one when it comes to, the real world and as well as the CTF challenges is the x86 architecture, which was developed by Intel a long time ago. So it's important to keep in mind that we're going to be mostly working with the x86 architecture, which defines how our assembly language is going to be, which defines how the instructions are going to be and everything. So now let's take a look at what some of these registers are. So here we have the EAX, also known as the accumulator register. It's used for storing operand and results data. EBX is the base register, it points to register. ECX is the counter register, loops operations. EDX is the data registers, it does input and output operations. The ECI, EDI are source and destination index for string operations. All of these registers, EAX to EDI, are known as the general purpose registers. And so the EAX to EDX have what's known as higher bits and the lower bits. So this 16-bit portion, this is a 32-bit register, and the 16 bits right here, they can be broken down into AL, which is the lower 8 bits, and the AH, which is the higher 8 bits. Now it's important to keep in mind that a hexadecimal value represents 8 bits. It represents 1 byte. So right here we would have 1 byte of data, 2 bytes of data, which is 16 bits. And then in the entire register right here, we'd have 4 bytes of data, which is 32 bits. If you remember from last week's forensics workshop, that 8 bits of data is equal to 1 byte of data. So these are our general purpose registers. What's really important, these are the key registers, as well as in binary exploitation, you're going to really see the importance of the ESP and the EBP, but the ESP is the current position of data or address within the program stack. So this ESP changes automatically based on the operation and where the data is. So let's say right now we're over here, but then we add some more data over here, and then so the ESP will change to here. Then if we were to subtract that data down to here, the ESP would come over here. So the ESP changes relative to what you're doing. But we need a register to always hold the base value of the frame. This is called a frame, so that we can refer to the other operations relative to where the base is, right? So the base is this base pointer, also known as the frame pointer. It contains the base address of the function's frame. And we're going to see how everything in the registers is relative to the base pointer. So this is an x86 architecture. So all x86 architecture use a stack as a temporary storage area in RAM. So this is a stack frame that allows processors to quickly store and retrieve data in memory. Higher memory addresses are at the top of the stack, and the lower memory addresses are at the bottom. So a memory address of 16 would be here. A memory address of 4 would be below that, and a memory address of -4 would even be below that. It's important to keep in mind that the stacks follow what's known as a LIFO method, a last in first out method. So things are pushed on top of the stack. So whatever is pushed on top of the stack last is popped up first. And that is because LIFO is, you could think of it like stacking plates. So let's say we have a register right over here, which is like a countertop, and we're going to put plates on it. So we put 1 plate, 2 plate, and so forth. And we keep stacking our plates. What's important to note is that we can't, if we want to retrieve the bottom plate, we have to take off all the plates that are on top of that. So the plate that we put on last would come off first. That's basically what a LIFO method is last in, first out method. So now let's take a look at how data is stored inside this x86 architecture. So data is stored using the little endian method. So let's say we had a hexadecimal value given to us that was 1, 2, 3, 4, 5, 6, 7, 8. So that value would be entered from the least significant bit to the most significant bit. And that is known as the little endian method, is when you're storing data from the least significant bit to the most significant bit. If you remember from our forensics workshop, the least significant bit is the rightmost bit and the most significant bit is the leftmost bit, because the least significant bit has the least value because it's 16 to the power of 0, 16 to the power of 1, and then this would be 0, 1, 2, 3, 4, 5, 6, whatever, 16 to the power of 7, right? So it's going from the lowest to the highest bit. So we would store it as 7, 8, 5, 6, 3, 4, 1, 2. So when you're taking these values out of the stack, you have to make sure that to know how they were inputted. So you have to convert them back to how they actually were. So you're not just gonna, when this is entered into a stack, let's say you're reading this from right here, when you take it out, this is not the accurate representation. You have to represent it the way that it was entered into the stack, which would be like this right over here. So also it's important to remember that in 32-bit registers, the memory addresses of the registers are 4 bytes apart. And we're going to demonstrate that right here. So right over here, we have our base pointer, which maintains the base of the stack, and everything is relative to our base pointer. So right here, we have the base pointer. So because our 32-bit registers and memory addresses increase by 4 bytes, this value right over here would be EBP plus 4. It's important, very important, that everything is relative to the base pointer, which is why for this one we'd have EBP plus 4. And the value over here would be EBP plus 12 because it's incrementing by 4. The value over here would be EBP plus 12, and then 12 plus 4 is 16. So the next value would be EBP plus 16 because we had to know what this base is plus 16. So everything is represented relative to the base pointer. And values below that, which are used to store local variables that are part of the program, would be EBP minus 4, EBP minus 8, EBP minus 12. But now when you're looking at when you're actually looking at a stack frame, it's important to keep in mind that these values are not going to be EBP plus 12, 16. They're going to be represented by hex. And we know that hex goes from 0 to 9. After 9, 10 is represented by A, 11 is represented by B, C is represented, 12 is represented by C. So then in a actual stack frame, this would be EBP plus C. It would not be 12 because it would be represented by the hexadecimal value. So in looking at these, it's really important to make sure that you're looking at, that you're understanding the hex and not treating it like decimals. Anytime if you want to know if something is a hexadecimal value, any hexadecimal value will have 0x appended to it or just x. When you see that, then you know that it's a hexadecimal value. So as mentioned, by using a base pointer, the return address will always be at EBP plus 4 because it goes right above. And then the first parameter will always be at EBP plus 8. And the first local variable, which is part of the program, will always be EBP minus 4. Now, when storing hexadecimal values into the register, it's important to remember that they're represented as little endian, but the negative integers in binary are represented in what's known as 2's complement. And we're not going to discuss the mathematics behind it of exactly how to calculate the 2's complement, but it's just important to keep in mind that they will be represented by the 2's complement if you ever come across a negative integer inside the stack. Now let's take a look at what some assembly instructions actually look like. So assembly instructions represent a single operation for the CPU to perform. So as mentioned before, This is the more human-friendly way to represent those instructions instead of just, reading a bunch of binary. This is more easy for people, for humans to understand because we're not a computer. So basically, what this is saying, move S into D. It's saying move the source into destination, add S to D, so add source to destination. These are just some examples. There's an exhaustive list of actual instructions, and the full list is right over here. So when you're doing these problems, you can always refer to this list right here when the slideshow is up on the CanHack Resource Hub. And then JE is jump when equal, JNE is jump when not equal, JG is jump when greater than. Now, in an instruction, you might see these values. You might see byte, word, or D word. Basically, byte is pretty self-explanatory. Byte means that only move a byte of data, and byte is just one byte, 8 bits, and this is what it would look like in hex. A word is 2 bytes, and this is how 2 bytes are represented in hex. These are 16 bits. So if you had to represent it in a register, let's just go back for a second. Let's just go back to this. So you would have 0, 0, 0, 0, and that would be 2 bytes. And so that would be, 2 bytes in the AL or in the AH, so the lower and the higher registers, the lower bits and the higher bits. A D word is 4 bytes, so basically whatever the full value that's in the register. And that would be represented by the 4 bytes right here, also 32 bits. So now let's take a look at how, when the stack is being set up, what exactly happens. Let's talk about the prologue, as it's called. And basically the prologue is what happens when the stack and registers are being prepared to be used within a function. So the prologue typically looks like this. Basically, these are the instructions. It's saying push EBP, which means push the current base pointer onto the stack so it can be restored later. So then we would have one right here. This is the EBP. It would be at the base of the stack, as I mentioned before. Everything else would be relative to EBP. This would be EBP plus 4, EBP plus 8, EBP plus 12. C is in hexadecimal, C is 12 in decimal. So the hexadecimal C is equal to 12 in decimal. And we know these are hexadecimal values because of the 0x. So basically that is the first thing that happens. It says push current base pointer onto the stack. Second, assigns the value of the base pointer to the address of the stack pointer, which is pointed to the top of the stack, so that the base pointer will point to the top of the stack. Right here is the top of our stack. And as we and the stack pointer is here and the base pointer is here. But as we add more variables, the stack pointer will move either up or down depending on what we're doing, but the base pointer will always remain here. And then the last thing would be to sub this whatever value right here for ESP. So that means moves the stack pointer further by decreasing its value to make room for functions local variables. So right now, pretend that only EBP exists, old EBP, which is right here. Only this value exists. None of this stuff on top exists or at the bottom. So we just have this value right here. We're pushing this onto the stack. So now we have old EBP, the base of the stack. Then we're going to move ESP into EBP, and ESP is pointing right over here. Now we're going to make room for, let's say, 16 local variables. We're going to make room for exactly 2 bytes, right? 2 bytes, not 2 bytes. We're going to make room for, okay, so sorry, as I was saying that, so we only have the old EBP right over here. We have the old EBP right over here. and everything will be in relation to the old EBP. So what happens is the old EBP comes onto the stack, and the stack pointer, this is the base of the stack. The stack pointer will also point to this. But let's say you make room. It says to make room for 4 additional registers. So we're gonna have to store, this amount of variables. So let's say that it was make room for 0x10, which is hexadecimal 16, which is decimal 16. So then what would happen is our stack pointer would move, and now it will point right over here. But our base pointer will remain here, and everything is relative to where the base is. This is called a prologue, and before when you're looking at assembly instructions, you'll see this action taking place. So just remember that this is just a standard that happens, especially with x86 registers. This is what it looks like. So don't get alarmed when you see this. This is just the basic standard thing that's happening. It's setting up the stack and register. So now let's try reading some assembly instructions, and let's try doing some problems. It's really important for these problems that everybody tries to do them at their own time, and take some time to do it yourself and get some practice, because they are a little bit tricky and a little bit challenging. But if you do it line by line, then and with practice it gets better. And if you make sure you have a strong understanding of how the stack and the registers work to really understand these problems. So this is our first problem. Let's actually take a look at what the PicoCTF website, says about this problem. So this is ASM 1. It says, what does ASM 1, this is the value we're given, hexadecimal 2E0 return. Submit the flag as a hexadecimal value starting with 0x. So it's not, this is not going to be in the normal flag format. So it's going to be 0x and then whatever the value is. So let's go back to this problem. And let's full screen this. Okay, so right over here, we have our prologue happening, our EBP, we're establishing the EBP, and we're putting the stack pointer at the base. So the stack pointer EBP right here, and there's just going to be a return address above the EBP, which always kind of tells you where to return to, and that's the location where you return back to restart the function. So as mentioned, this will be 0, and then EBP plus 4 will always be your return address, and then the variable, any data will come on top. So the data we were given is 2E0. So we push that 2E0 on top of the stack, and obviously these two values are taken. So it goes into EBP plus 8, which because it goes into 8 because remember this register increments by 4 bytes. So what's 4 plus 4? It's 8. Everything is in relative to the base pointer, which is why it's EBP plus 8. So this now is 2E0. So that's our first, we push that on, and now we have our stack. So what's the first instruction that we have to do? CMP stands for compare. So what this is saying is compare, and remember that D word is 4 bytes of data, which is 32 bits. So it's saying compare all of the 32 bits that are in this register, 0 EBP plus 0x8, so 2E0. So compare all of the 4. In this case, we don't have 32 bits. We just have 8 times 3, so we only have 24 bits, right? We only have 24 bits in this case, but that is just a precaution. So we're going to compare these with hexadecimal 3FB. Okay, so when we compare 2E0 is smaller than 3FB, is an easy way of doing that is if you're not good with hexes, to converting both values to decimal values, and that might make things a little bit easier. So when we compare 2E0 with 3FB, we realize that 2E0 is smaller than 3FB. So then JG stands for jump if greater than. So if our data 2E0 was greater than 3FB, we would have jumped. But we're not going to jump to this location 37 because 2E0 is smaller. So we're going to continue going down the instructions. Now we're going to compare 2E0 because that's the data that's in this register EBP plus 8. We're going to compare it with 280, hexadecimal 280. It says jump if not equal to, and obviously 2E0 is not equal to 280, so we're going to jump to this position right here. This position right here, we're going to take all of the 4 bytes that are in EBP P0x8, hexadecimal 8, which is 2E0. We're going to take all of those bytes and move them into the EAX register. So now our EAX register has a value of 2E0. Now we're going to subtract 0xa from whatever is in the EAX register. We know that we have 2E0 in the EAX register. So when we subtract, and don't do this manually, you can use an online calculator. So I think, let's see where I have, oops, I did not mean to do that. I did not mean to do that, sorry about that. I just want to go to a hex calculator right here. So let's do 2E0 subtract 0xa. When we subtract that, we get 2D6. So when we subtract that, we're going to get a value of 2D6. Now it says jump to, after we have that value, jump to 60. When we jump to 60, we're just going to pop the base pointer and return. So that means it's going to start all over again. So what we end up with, what our flag will be, is 0x2D6. So I hope that was clear. I know it's a little bit challenging, so make sure that you rewatch this recording and try it yourself. And if you want, you can try using different numbers, seeing what happens if, right over here, if it was greater than, give it a value that is greater than and see what happens then. If we did have a value that was greater, we would have jumped to 37. At 37, we'd have to compare that whatever is in this register with this value. And then if not equal to, and if it was not equal to, we would have jumped to 54 right here. We would have then taken the 4 bytes and moved them into EAX. We would have added A to EAX and popped. So just try to see what happens with different scenarios and try to make sure you get some practice with this problem. It is a little bit tricky, but with practice, it will get more clear. And also make sure you have an understanding of what the stack looks like, the prologue, and how the base pointer and the stack pointer work. Let's look at ASM2. So let's just take a look at what the ASM2 problem reads. ASM2 reads, let's see where ASM2 is, right here. ASM2 says, what does ASM2 hexadecimal 4, hexadecimal 2D return? Let's just make the screen bigger. So that is our problem, and we're given an ASM file. So the file that we're given will be shared on the screen right now. So this is the file that we're given. So basically, as you see, the prologue is happening right here, and this time we are making room for additional registers, so our stack pointer will have to get moved. And the values that we have to push onto the stack, the data is hexadecimal 4 and hexadecimal 2D. So let's forget about all of this and let's just go ahead with the prologue. So the prologue, we have our base pointer right here. The stack pointer will also be right here when we push it on right here. And now we're going to push the data on top. So we're going to push the data on top. So we're going to push the first value comes first, and then, so it's, remember, it's last in, first out, and this would be the last value added. So because we're incrementing by 4, after we push EDP plus 8, which would be this value, we put it into that register, the next one would go into 8 plus 4, which is 12, and 12 is represented by C in hexadecimal. So that's what our stack would look like without any of this stuff happening. Next, what this is saying is reserve 16 bytes on the stack. So let's just reserve 16 bytes right over here. These are the 16 bytes. And when we reserve those 16 bytes, our ESP will now point to right here, but our EBP will remain right over here. Because it's the base pointer, everything is relative to that, but our stack will be right here because it's moved to now here. So now let's start with the actual problem and see what's going on. So now it's saying take the 4 bytes that are in this location, which is 12, and move them into EAX. So we know at this location we had 2D, so we're going to take 2D and move it into EAX. So now our EAX value would be 2D. Now it's saying whatever is in EAX, move that into this place. This is where the local variables go. So we're putting that into EBP minus hexadecimal 4, which is right here. So now our new value here is 2D. Now it's saying take whatever is in this register right here, plus 8, and move that into EAX. So we're going to put that E into EAX. Now our new EAX value is 4. Move whatever is into EAX into this register right here, and that is going to be right here. That's going to be our new value at 4. Now it's saying jump to 31. Let's see what happens. So when we jump to 31, we're going to see it says compare whatever is in this register, and we know now that it's 4 because we moved it in the previous actions to this value right here. And if it's less than, jump to 20. So when we jump to 20 right here, we're going to add plus 1 to this and plus D1 to this, and we're going to compare again. We're going to compare if that value now is less than 5FA1. And you know what? It will be. So then if it is less than, we're going to go back to 31. We're going to jump if lower than to 20. So we're going to go back to 20. We're just going to we're going to end up in this loop. So let's see what happens. It says add. So let's say we're back here, back to where we were. It says jump to 31. So now we're back at 31. First, we're going to jump back to 31, and we're going to see if the value is less than what's here. And it was, because the old value at E8 was not D5, it was 4. And if it was less, then jump to 20. So we're back at 20. And when we're back at 20, we're doing the same things over. We're adding 2D, because that's what the value was in this register, to 1, and we get 2E. Now we add D1 to whatever value is in this register, and that was 4. We get D5. I'm just using that same hex online calculator that I showed you earlier to do these additions. I'm not manually doing them. The D5 is less than this, and then, you know, we're just gonna stay in this loop until we figure out what value can we store in this register that is going to be greater than this place, this F5A1, because if it's greater than, then we won't have to jump, and we can move on and finish the rest of the instructions. So let's figure that out, because we're going to be because we can do that manually. We can keep doing it and we can keep adding and incrementing the register and jumping. But why should we do that when we could save ourselves times and just do some basic algebra to figure out what value that will be? So like I said, it's easier to calculate how many times D1 needs to be added into this register so that we can so that we don't jump, actually, so that we can move forward. So let's go into this place to do the algebra. So let's come up with a simple algebraic equation. We're going to do that D1 times a variable Z plus 0x hexadecimal 4, because that's what's in the value to begin with. That's what we started off with. We stored it in there, is equal to 5FA1. What's going to give us something that's equal to or greater than? Then we're just going to do some basic algebra, and we're going to end up getting that that variable is 75 remainder 18. It's still not going to be greater than or this value, so we need to make it one more so that it's greater than. So z needs to be greater than 75, so that it will have to be 76. So now we know how many times we need to do this loop. We need to do it 76 times to get out of it and to be able to go on to the next instruction. So when we do this loop 76 times, these are the values we're going to get. So the value that at this register right here is going to be D1, sorry, 01x times 76 plus 2D, because that is the old value, and we're going to end up with hexadecimal A3. Before that, we have to figure out what value we needed at this location. So then we're going to do D1 plus 4, because that's what was in this register right here. It's equal to hexadecimal 605A. So let's go back just one second. So we needed to figure out what value at this register, how many times we have to do this so that the value at this register that gets added to here will be greater than this. So the value here was 4. That's why we're going to do 4 plus D1 times 76, and it gives us 605A, which is greater than F5A1, which is greater than, so we don't have to jump. If lower than, we can go into the next one. But the next one is saying move this value that's at this register into EAX. Now to figure out what this value is, we have to do the same thing. We have to multiply that by 76 times. And the value at that register was going to be, so we're going to do EBP 0x4 is equal to 1 times 76, because we're adding this 76 times, plus 2D, because 2D is the old value that was in this register. And we're going to, using a hex calculator online, we're going to get hexadecimal A3. So now we know that by doing that loop 76 times, it gave us a value that was greater than this number, so we didn't have to jump, because the jump value is jump lower if less than. And as long as that value over here was less than this value, we would have to keep doing it. We figured out how many times we needed to do that, which was 76 times. When we had that value, now we can finally move out, and the value that we finished off with was hexadecimal A3. So that was a little bit tricky and challenging. Just make sure that you draw out the stack and you keep monitoring what's going on with the stack. And so now, obviously, when we have at this values our stack pointer, wherever, like here, our stack pointer would be here, and then over here, our stack pointer would be here, and our base pointer would always remain over here. Now let's take a look at an even more challenging problem, but this is going to be the last assembly instructions problem that we do for today. So let me just minimize this so that we can go into the Pico CTF platform and see what exactly that is. Let's go to ASM3. Maybe I left it in the previous page. I did right here. So what does ASM hexadecimal D73346ED, hexadecimal D48672AE, and hexadecimal D3C8B139 return? So now our problem has gotten more complex because we're going to have some assembly instructions, and now we have a 3 hexadecimal values to work with. So it's going to be a little bit more tricky. So let's take a look. Well, there's not too much going on in this function, which is nice because it makes our lives a little bit easier. There's not too many instructions, but this will be a little bit of a challenging problem because we have to keep in mind a lot of things. We have to keep in mind how hexadecimal is stored into registers. We have to keep in mind how negative numbers are stored. We have to keep in mind what these byte, word, and what these exactly mean. So let's get started. So the first thing we're going to do is we're going to set up our stack like we've been setting up for the previous two problems. We're going to start off with establishing the base pointer. The return address goes on top at the EBP plus 4. Everything is relevant. Everything is in relation to EBP. So the return address is at EBP plus 4. Now we have 3 values which all will need to increment by 4 bytes. So at EBP hexadecimal 8, this first value will need to be inputted. But remember, we mentioned the little endian mode. When we're inputting hexadecimal values into the register, we have to make sure they're going in little endian mode, which is least significant bit to most significant bit. So we're going to start off with ED 4633 and D7 going from the least significant bit, and in this case the bytes. This is 1 byte, 2 byte, 3 byte, 4 byte, and putting them into the registers. The next, we're going to have this value, and again, we're going to flip it over, and this is going to be placed in 8 plus 4, which is 12, and in hexadecimal 12 is C. So we're going to have AE 7286 D4, and then this last value right here will be put into hexadecimal 16. X10 in hex 10 represents decimal 16. Because 12 plus 4 is 16, and remember our registers in x86 increment in a 32-bit register by 4 bytes. And 64-bit bit register is 8 bytes, but this is a 32-bit register and it's an x86. So now we have our stack all set up. So we have our stack all set up. Let's go into the further instructions. So we've done that. Now let's talk about what XOR EAX means. XOR EAX would set the EAX register to 0. It's just a way of clearing the register. Don't worry about that command too much when you see it. If you ever see command and you don't know what exactly it means, just Google it. And like I hadn't seen this XOR EAX, and when I Googled it, I read about it, and people said it was an easy way to clear the register, so it just sets the register to 0. Now, if we remember, byte, there was 3 things. There were byte, word, and D-word. Byte was 1 byte, word was 2 bytes, and D-word was 4 bytes. So a byte is this, 2 bytes is this, and a D-word would be the entire thing. From a few slides ago, actually. So after we've set the EAX to 0, we're going to move 1 byte of data at the A location into the higher bits of the EAX register. Now, remember that hexadecimal, it goes from 0 to 9, and then 10 is represented by A. So right over here, we have the 8 bytes and the 9 bytes, and then here we have the 10, and it's asking us for 1 byte, and that would be 1 whole byte. 33. So what it's saying is saying take 33 and move it into the higher bits of the EAX register. So right here, we put it in and we have 33 into the higher bits. The next instruction, it's saying shift to the left, shift AX, which is this entire EAX register, shift to the left by 16 bytes. Why 16? Because 10 is hexadecimal 10 is equal to 16. So when we end up doing that, it clears out the register again because this would go out all the way. So again, the register gets cleared. So now let's go on to the next register. So now our EAX is just 0, 0. It's just all clear now. There's nothing in the register. Let's go on to the next instruction. The next instruction is saying whatever is an AL, so AL minus the byte, which is at 0xC. As we know, hexadecimal C is equal to 12 in decimal, and that is this byte right over here. So 0 and the location at the lower bits of our AX register, EAX, is we know 0 because we just cleared the register in the previous step. So we're going to do 0, 0 minus AE. Now that's going to give us obviously negative AE. But now we have to remember, and we talked about this in a few slides before, that for negative hexadecimal numbers, we have to get the 2's complement, which for negative AE is 52. I use an online calculator to get the 2's complement. Let me just find, and this is the calculator I use. So I just put in AE and I would get 52. So that's how I knew. I didn't do any crazy math to get that. If you do it manually, it's really it's time consuming. So I suggest you just use an online calculator to calculate that. So now it says to place the 52, this value into the lower bits of the EAX register. And we know the lower bits are right here. This is 16 bits and this is the entire 32 bits. So it says to place the lower byte. Byte means 1 byte. So we're placing 1 byte, which is 8 bits, into the lower register. So 52 goes into here. Now the next thing is to take AH, which is 0 right now, because we know from previously, AH is 0, right? AH is 0. Now it's saying that take the byte that is at D, and as we know what D will be, C is 12 and D is 13, so obviously D is 7-2. Saying take 7-2 and move it into the AH register, the high bits. So add that, and when you add that 0, we're just going to get 72. So 0, 0 plus 72 is equal to 72. So now our EAX register has 72 and 52. 72 in the higher bits and 52 in the lower 8 bits. And this gives us 16 bits or 2 bytes. Now, the next thing that we have to do is we have to exclusive OR, which is a logical function, the entire EAX register, not the entire thing. Word means 2 bytes. This is 1 byte and this is 2 bytes. We have to take the 2 bytes of the AX register. AX, so AX, when this is EAX and this is AX right here. This is AX. Take the 2 bytes of AX register and exclusive OR them with the bytes at this 16th value right here. And we know that 16 is right here. So we're taking 2 bytes now because it's word. Word is 2 bytes, D word is 4 bytes, as mentioned in a few slides ago. So we're going to take 39 and B1 and exclusive OR it. But now we have to remember that when we were putting it into the register, we put it in little endian mode, but when we take it out to do anything with it, we have to flip it back to its original format, which would be B139, going from most significant bit to least significant bit. And when we exclusive OR that, we're going to get this value. You can use an online calculator. I just used an online calculator. Let me show you how I found one. I just did, let's go into Google actually, because I don't know, DuckDuckGo doesn't give me the best results sometimes. XOR hex calculator. Okay, so I've used this one before, so that's giving me hope. So 7252 exclusive OR, and what is the value? B139. C36B is going to be your answer. So it's going to be hexadecimal C36B. And after we get that, this means no operation. We're going to pop EBP in return. So this is going to be our final answer. Now, when I was doing this, there was a lot of things that threw me off at first when I put the values in. I just forgot that I had to put them in little endian mode first. So I put them in regularly and then I did it. And when I put them in regularly, obviously it changed these values. So I got the wrong answer. Then I tried again and I remembered that I had to put them in little endian. But then the last thing that I was not getting the right answer was that I was not taking these values and flipping them back to the way they should be. And I was like exclusive ORing it with 39B1, and that's just going to give you a different value. So when you do these type of problems, you have to cover all your bases and make sure that you look at it in a lot of detail and make sure it's very specific. Even this byte or word or D word, you have to make sure that you understand byte is just 1 byte, word is 2 bytes, and D word is 4 bytes. It's really important to understand that. Next time, we're obviously going to be looking at a more easier way to do these problems, but for this class, it's really important we can break it down without using any tools. So that is a little bit about assembly language and ASM, and you saw that it can be definitely challenging. So we did cover a lot of challenging materials today. So now let's finish it off with something a little bit less confusing. So let's talk about Android reverse engineering. So Android reverse engineering is usually reverse engineering APK Android package kit files, which are the app files. So APK file is an app created for Android, Google's mobile operating system. So when viewing these files, you can view them on your phone if you have an Android, and if you don't, you can view them using an Android emulator, which would mimic what an Android would do. So reverse engineering, what's the purpose of reverse engineering APK files? Well, it's to better understand how an app or the features work. It's to determine if there's anything malicious taking place on the app. If libraries that are being used, like again, breaking down the program and seeing what's happening within the app. So tools for Android reverse engineering, and these are tools I recommend getting. So Android emulators, it simulates Android devices on your computer. And the one I use is called Android Studio. It's by Android. There's other ones, but I feel like I trust Android Studio more because it's developed by Android. And there is some other open source great emulators, like it's called JDP Lab or something. There's a lot. So if you Google them, you'll be able to find one that can work with your system. But Android Studio was compatible with my computer, so I installed that. And then you would need a decompiler for APK files. So there's JADX and APK tool. I use JADX because I just like the way that it looks, because it has a graphical user interface, and APK tool is a command line only. So let's look at what the problem asked for droids 1. So for droid 0, where do droid logs go check out this file? And this file was an APK file. And I've attached a screenshot of what happened when I took that file into an Android emulator. So because we are short on time, I will not demo droids 0, but I will demo droids 1 because it's a little bit more challenging. So this is droid 0, and this is my Android Developer Studio. So when I ran the app and I looked at this logcat, which was giving me the log output because that was the hint, I saw that this there was a flag, and this was the flag. It said Pico CTF, a moose once bit my sister. And that was very easy. All I had to do was open the file, run it, put some text into here, into the app, and it was running. So now let's look at Droids 1, which is find the pass, get the flag. So it says find the pass, which obviously means find the password, get the flag in the file is a APK file. So now I'm gonna see if I can run Android Studio for you guys, and if I can run this file. The tricky thing with Android Studio is that it does take a while to load, and it does use a lot of, it uses up a lot of your CPU when you're using it. So it is tricky. I'm also gonna power up my, VMware, sorry, my virtual machine, just so that I can show you guys the JADX tool. So let's open up my, okay. So let's just open this. I think I saved an instance of that app so that it wouldn't take so long to load. So hopefully it will load it up for me again. And if it doesn't, then it takes a few minutes. Let's just exit text edit. And it is reopening my files. Trying to see what is happening and why this is not launching. Okay, perfect. So it has opened up. Perfect. This is great. So now what I'm going to do is I'm going to open up an emulator. Let me just see why this will not launch. Perfect. So that is launched. So now I'm going to show you what the JADX backend looks like. And then I will show you why it's useful. It allows you to view the APK files in detail. So I downloaded that. There we go. Let's see what it was. So I'm going to use the GUI for that. Hopefully it opens it up. And let's use, this is the file that from Pico CTF. So it said that, can you find the password? So now I'm going to analyze what's going on in here. So let's see. Let's see if I can see what's happening. So where, does anyone have an idea of where the password might be? Does anybody know where the password might be? Let's look at this flag thing. Okay, so here is the code for the flag and the user package. And this is, yeah, it might be in the source code. That's a good guess. So let's see. As you can see, it has different architectures, x86, which might be haunting some of you right now. So let's really see. You have to play around with it. I was playing around with it and, trying to see what exactly where it would be. It was confusing to find. Let's look in values. Okay. Well, we know passwords are strings, right? So check out if it's in the strings. So let's see. Pico CTF. Oh, I see it. It's right here. It says password. So we know that is the password is opossum. So now let's go back to our Android Studio. And to run an app in your in a emulator. So what I found was that this Pixel takes up, for some reason, it's very, very slow when I use the Pixel. So I'm gonna try using the Galaxy Nexus because it works better on my computer. So it's gonna now open up the app. And this is the part that takes a while to load. And we are getting close to an end. So let me know if you guys want to see this or if you just see a screenshot of it. Let's just restart. And I'm just going to close this so that it does not. Okay, so here it is. So it loaded from the last state that I was in. So I put in the password here. And when I put the password here, it gave me the flag right there. It's restarting now, but hopefully you guys saw that. So all you had to do for the second problem was to analyze the strings or analyze the source code and analyze the files to see where the password would be stored for Droid 1. And then after you find the password string right here, you use an emulator to input the password and get the flag, which would be right over here. So this is definitely one of the more easier problems. So now here are some resources, and I will copy and paste all of them into the chat. And also the slides will be uploaded after the presentation. You can click them at any time, but these are some really good resources for assembly language. And if you were confused by some of what we did today, these really highlight and go into detail. I love all of these resources. They really helped me to understand some of these problems. So I'm going to paste them into the chat. And of course, thank you so much for your time. And if you have any questions, please let me know. If not, you could feel free to leave. And we're going to be discussing binary exploitation next week. And if you have some time, do go over some of the register stuff because it's important in binary exploitation as well. How long do you think it will take to master? Honestly, it will not take that long, I promise you. If you look at, no, I don't know about mastering, but looking at a problem and analyzing like the way we did today, it shouldn't take that long if you maybe dedicate a couple hours every day to really practicing the problems. I 100% know that in no time you will have those problems mastered and you will really understand what you're doing. It just takes some practice. So these are all of the links. And I will also share this link right here. This is for two's complement. Yeah, so that's why it's really important to be familiar with hex. Not that familiar, just to understand where like the locations are, like, and to not let it confuse you, to just look at those as addresses. I know it can be a lot of like numbers and overwhelming amount of just numbers on the screen, but to look at them and see them just as a memory address, and to not let the values in there confuse you. So I think I've shared all of the links, and so yeah, so if you have any questions, please feel free to stay. And if you don't have questions, feel free to leave. And we will be doing binary exploitation next week. Yes, so for all the resources of all lessons, they're all posted in the CanHack, the DMZ CanHack resource hub, and I will show you where you can access that right now. Okay, so DMZ CanHack resource hub right here. So all of the recordings and the slides are on this, located here in the DMZ resource hub. So we have all of the presentation slides. And after this workshop, we will have the reverse engineering one posted, and we also have all of the recordings. I'm going to quit this because it's slowing down my computer. So this is where you can download all the files, and Madison has added it in the chat. So again, thank you everyone. If you have any questions, we are here, and if not, then please feel free to leave. So there's a question about, I get everything except starting the ASM programs. I don't understand how you know which values go where. Like in the last one, why didn't you start at 4? Why wasn't it 8, C, and 10? Not sure if there's a good place to look that up. Yeah, for sure. So let me just go back into that and explain it a little bit more. So let's look at the last problem. So basically, this is an x86 architecture, and the way that it works is the addresses increment by 4 bytes, or by 4, the values of 4. So it always starts off at 0, and at 0 we have the old EBP. Let's look at this chart right here, which explains it. We have the old EBP, and then we have your EIP, and EIP is the same thing as your return address, like how it was put. And so this is 0, and then this one, because it increments by 4, it's 0x4. And because it's 0x4, it's already taking, these places are already taken up. So the next one after 4 would be 8, and then 12, and then 16. So we always will start, for most cases, at 8. So if we go back to ASM1, we also, when we inputted the value, we started with the 8th because there was already these things in these two positions. Then when we go back to ASM3, we had already this old ABP and the return address, and then we started off with this value and we input it into this location 8, and then it increments by 4, so then we put it in the 12, and then it increments by another 4, so then we put it into 16. What's important is to not get confused with these values. They're not in decimal, they're in hex. So this is 4, 8, 12, and 16, so it's incrementing by 4. And EAX is a separate register, which is not the same as EBP, if that makes sense. Okay, I'm glad that cleared that up. And you can always go back to the recording and review it again. This is a challenging. It takes a while to get it. I had to practice these problems myself a few times before I actually was able to get them. They're very tricky and challenging. I hope that makes sense. And if you have any questions, we are here. And if not, please feel free to leave. Thank you, everyone.